Okay, want to talk about this week's lab. It says make a project called ADC DMA so you can copy over your project from ADC int and do the copy paste, rename the IOC file, do a project clean, and then you should be able to build it and have just what you had the week before as far as interrupts. We don't have to change too much to make DMA happen. There's a whole bunch of structures and things that are filled in automatically by selecting some of the things we're going to select. It was quite challenging to set up before we had the graphical environment doing it all for us, so much so that I would just print out a page of here's the different structures and here's what you need to put in them in order to make it work right, because somebody would miss just one little thing, everything looked great, and the DMA wouldn't work. It's all kind of taken care of pretty much for you now, and we'll go through that process. It says both the thermistor and the internal dye temperature sensor need to be read using DMA. So again, our direct memory access, we're going to have a separate piece of silicone that will go and get the conversions and put them into memory locations for us. It says you should blink the orange LED at a half-second rate. Again, showing us we have a heartbeat, something is happening there. Typically, you put one of these in a project, especially if you have a multiple tasks, just something that's running that shows you that your code is actually going and that it didn't get locked up somewhere. Continuously read 100 values of each using ADC1 and average them. So you've used ADC3 and ADC1, two different ones. Now I want you to just use ADC1. So you're going to read both things on two different channels, and then we're going to average them. Print your thermistor and your dye temperature to one decimal place on the SWV ITM data console. And so, our thermistor pretty standard on the values. Depending on the board, the one I have here I think reads around 31 degrees. I have one that reads 55. I have one that reads about 70. And again, it could, in the documentation it says plus or minus 40 depending on what yours was, but it should be pretty consistent after that from whatever your base temperature is. So if it goes up 5 degrees, if you can make it 5 degrees warmer, it should read 5 degrees warmer. So I'm not so concerned of there, but we should be somewhere. I've seen 30 to 60 degrees is where you should be, I think. If you're getting something in the hundreds of degrees or very, very small, then there's probably something else going wrong. I then want you to display your temperatures on the default graph in something known as the STM32 monitor. They used to have an STM32 visual development or monitoring system, and they've since gotten rid of that, and they have this STM32 monitor. And I was quite surprised to see it. It's about maybe a year and a half ago or now that they've gone over to this. And essentially what they've done is they've embraced IBM's open source Node-RED. And I don't know if any of you have seen it. We'll talk a little bit about Node-RED. So they packaged that up and said, oh, you can do so much more than our display software did with being able to utilize the capabilities of Node-RED. So it's now bundled in there, and I'll show you a very little bit of some of that coming up here. And so that's what we want to do. Says make sure your main.c is documented appropriately, upload that as main.txt, upload a demo of your SW ITM console and your monitor by the start of lab week 6. So I want to see, just your output like there. I want to see always the main.c file. If you have demoed and got signed off on the sheets, then I am fine with just giving me your code. If you didn't have that, then I'd need to at least see a video of the demo and things running. So and you have till next week's lab to show that off. Okay, now I want to look over at, first of all, the, well, look here. This is the STM32F407 data sheet, and it is over on page 19 of 203, and it's this block diagram showing us our 407 chip. And so I like coming back to that to get an idea of where things are. And what I'm looking in particular is our DMA controllers. So I have, it says DMA1 and DMA2 here, and it says 8 streams, first in, first out, the buffers, and it goes to the advanced high-speed bus. And so I have another piece of silicone, just kind of like I also had when I had my nested vector interrupt controller, to be able to, an external thing to be able to handle different interrupts and provide something to the ARM CPU. We have this extra piece of silicone, and DMA stands for direct memory access, and it's essentially a sequential state machine. You will set it up to say how many bytes you want to move from one place to another and say go, and it does it, okay, without your CPU having to so copy this and then write it here and copy this and write it there. It can do that. Now, in amongst the DMA, there's also something known as a bus arbiter, because a DMA controller is a bus master, so it can take over the bus. It can go and control where things are. But your ARM CPU is also what's known as a bus master, so it again can take over the bus. So you have all of these devices that are able to take control of a bus and be able to move data across the bus. And so you have something known as a bus arbiter that says, okay, DMA1, DMA2, and the CPU all want the bus. Who gets it? And not only that, but it could say, well, you might want to be able to move something from a GPIO port into maybe a USB, and maybe it won't involve what another one will do, and it can use another set of buses that aren't being used. And this arbiter takes all the different needs and figures out who gets the bus and who has to wait. Okay, there's a lot of complexity there. It's done for you. Okay, and so what I need to do is have a look at using DMA1 and DMA2 and how I'm going to use that. If I go look at the reference manual, the 1700-page reference manual, section 2 talks about memory and bus architecture. And it says STM32F407, the main system consists of a 32-bit multi-layer advanced high-speed bus matrix that interconnects different masters. And so those are the things that can take control of the bus. And we have the actual Cortex M4 with a floating point. And so it can, your ARM CPU can go and take over the bus and be able to read and write stuff to various places. But the DMA controller, the memory bus, DMA1, DMA2, and also DMA2 controlling the peripheral bus. There's also another DMA controller that can handle Ethernet. Ethernet has lots of packets, and again, there's Ethernet on board. You just need the physical interface, the actual magnetics to go and put it on the line if you were to plug in a wired unit. Also, USB on the go also has a high-speed bus as well. So all of these different bus masters, any one of them can say, I need to talk to port B, or I need to talk to SPI or something like that. Then there's the different slaves, and so we have internal flash memory for instruction and for data. We also have static RAM as well that you can have as being destinations for these. We also have the advanced high-speed bus peripherals, including the bridges to the advanced peripheral buses. And when we looked over on this one, on the data sheet, this is the advanced high-speed bus, and you see it's going over to static RAM and it's going into flash. And then down here, we have the advanced peripheral buses going to the different ports in the ADCs and things like that. So these will send data down those different paths. Now, The bus matrix provides access from a master to a slave, enabling concurrent accesses and efficient operation, even when several high-speed peripherals work simultaneously. The 64 kbyte core couple memory is not part of the bus matrix. There's a 64K area for other things that's not on this, and it'll show being off to the side. See, this is saying there's a section of RAM that's not part of this. But the rest of this is saying, okay, we have these different, we have our Cortex CPU, we have the different DMAs, Ethernet, and they all go into this matrix. And then you have the bunch of the different slave devices. So you have flash memory, static RAM, the different buses, peripheral buses going out to ports or A to Ds or what have you, and this flexible static memory controller as well. And so it looks at all the different needs and what can I send where. You know, I could send the ARM Cortex out to the FSMC at the same time. DMA1 could be sending something out to one of the peripherals, and as long as you're not trying to use the same bus at the same time. And again, there's this bus arbiter that says who's most important and who gets it and where it has to take turns. So another piece of silicone, again, kind of complex to set all this up and put the right thing to the right place. The graphical interface makes most of it done for you, and so that's kind of nice. And let's go over and have a look at, I want to go to,
ML, are you recording right now?
yep. I don't know if you guys are finding them useful, but I try. That's why I have the earpiece on. Yeah, man. Okay. Okay, so nothing's changed here. We've got the thermistor there. If I go and look at analog, this time though, I'm going to, well, one thing has changed actually, because that was on 3, right? Whereas I put it on just, it's just on ADC input 1. Because if I go over to ADC input 1, I have input 11 and input 16. So before I used 2 different ADCs. This time I'm just going to say, well, we have 16 channels on that I can use on each ADC. So let's try put them on 1 here. And so what I want to do then is look at my parameter settings. Now I have 2 on 1. So there's a couple of things I want to do that are a little different. And one of them is scan conversion mode. I want to have enabled. And sometimes, for instance, that'll be grayed out unless I have multiple channels. And then it says, okay, you have the ability to scan. I want continuous conversion enabled. And so I want it to keep going. With DMA, we have this other bus master that is able to go and do things behind the scenes without my software taking over. So I want to just say, just do it forever. We could just say, use the DMA, do it once, put it in a while loop, and keep having our software do it. But the whole thing about this separate piece of silicone is I can just say, just keep reading me values. So I want 100 values of my internal die temperature. I want 100 values of my thermistor and just keep reading them. So 100 values of each. Just cycle through as fast as you can and just stick them to some memory location. And then what I'm going to do in my while one loop is I'm just going to go to that memory location and I'm going to pick out my die temperatures and pick out my thermistor temperatures, add up the 100 values and average them. Okay, and then go and print them out. And so continuous scan mode means, okay, I'm going to look at a couple of different channels. So I'm looking at those 2 different channels. and then continuous conversion, because I just want to start at once above while one, and then have it go on forever. DMA continuous requests I want enabled, because as soon as you have got some values, I want the DMA controller to step in and move it over to my memory locations. Now, number of conversions, I have 2 channels. I've got 2 conversions that I need to happen. As soon as you say that, it's a drop-down box. It's this box here, and it'll go. So when I do that, I can say, well, how many conversions do you have? And I'm just going to have input 11 and then the temperature sensor. So I have 2. As soon as you put 2, then this is going to drop down here, and it's going to say rank. Okay. By default, you'll just see rank 1. But as soon as I say 2, I've got 2 different ranks. And if I look there, and I'm going to highlight that, then it's showing me the different ranks. And so each one of these, I can go, oh, well, the first thing I want you to read, is it channel 11 or is it the temperature sensor? So I get to select which ones I want. And I could go, rank 1 is channel 11. Say I want 4 conversions, or let's say 3 conversions, and say rank 1 is channel 11, rank 2 is the temperature sensor, and rank 3 is channel 11 again. So I can read back and forth all of these different ones for whatever reason I need to. Okay, so it's a matter of just saying, okay, well, I'm going to read the channel 11 first, which was my thermistor, and then I'm going to read the temperature sensor second, and then the sampling time, by default it's at 3 cycles. I'm just going to make it a little longer. I'm going to go to 112 and just give it some time to sample between doing each, because this thing can go as fast as it can. So I'm just wanting to say, hey, just slow up a little bit, give it time for us to read in from the temperature sensors. And now this, if I had both on one channel and it was an interrupt, if I did it, the DMA can handle it, but if I did it on the interrupt, it would happen so fast that you would mostly be in the interrupt. You wouldn't give it enough time to go do other things. And so you'd find, okay, all of a sudden things don't work anymore. And it's because, well, it's doing the conversions and you're jumping into the interrupt routine, and that's all you're getting done. Okay. So ADC settings, we have scan conversion mode enabled because we're going through multiple channels. Continuous conversion because I'm only going to ask to start this thing once and it's above while 1. Okay, and then when you're done, I want the DMA to go and grab the data and move it. Okay, so those are the things that I've done. As far as the number of conversions, we wrote the number of conversions, the number of channels I had, and then I picked the ranking. So the first thing that I'm going to read in is going to be channel 11. The next thing I'm going to read in is the dye temperature, and then we go on from there. I don't need, from before you had the ADC interrupt going, we don't need that. But I have DMA settings, and it's going to set up an interrupt over for the DMA settings. And when I go to DMA, you'll have nothing here. And if I click on it, you are going to see, see if I can move it over a bit more. Okay. Okay, if I go add, you just go add. I don't have one available because it's right there. Well, let me delete it. I'll go delete. Let's go add. ADC1, that's the only one I have turned on right now. It automatically knows what DMA controller to use and what stream to attach it to. And so we say, okay, if I want to read DMA2, then it's going to be peripheral, the ADC, over to a memory location. And so we go there, I just click on it, and then it gives you some other options here. And so I'm going to go to circular, first in, first out, oops. And then most of the rest of it would be fine. Now peripheral, in this case, my peripheral doesn't say increment address, but memory it does. Okay, and the reason for that is my peripheral, the ADC, the result register is at a certain address in memory, and it's always the same place. I'll get new values, but it's always the ADC result register that I would read from. So you never want the DMA controller to go to the next address or the next address or the next address, because it's always at the same place. You're just getting new values. And it knows that, and it didn't check it off. And so memory, though, it says, okay, when you put something in memory, do you want it to stay there, or do you want it to continue on? And so I say on the memory, I want to make a buffer of so many locations, and so I want it to increment through that. Okay. The other thing here, which can get you messed up, is by default it knows that the ADC, that the data coming back is in a 16-bit. It's a 32-bit register. The upper 16 bits are reserved, so a 16-bit value is coming back. So it says really all you need is a half word for the information to be coming back. The libraries that you use with HAL, anytime we've gone and highlighted the libraries, it says that it's a uint32t. It's a 32-bit value coming back. Okay, and it's fine if I go half word. I just have to make sure that I am making an array of 16-bit values. If it's a whole word, then I have to make sure it's an array of 32-bit values. Because if I say that my array that I'm going to store everything in is 32-bit, and this stores 16-bit, it'll go 16-bit and 16-bit and put two 16-bit values in a 32-bit word, and all of a sudden it's really, really big. Okay? And so they just have to match up. So one of the things about the libraries, if you use half word, is it will give you a little exclamation mark going, you know, our library says it's 32-bit and you have 16-bit, so it's going to truncate it. It's going to, and it just gives you a little warning. So if I want to, if I'm wasteful and want to just say, hey, let's just move 32 bits at a time. The upper 16 bits are reserved. If we go look at the ADC register, the upper 16 bits are reserved. The data is actually coming back in the lower. Okay, you can put it. I'll show you where when you go and do it. You can put it as 16-bit values, and then you're using up less memory space. The library is just going to give you a little exclamation mark that says, are you sure you want to do this? Okay, so either way. Okay, so the one thing though I want to make sure is that you use a circular buffer. I haven't checked lately, but it wasn't working correctly. It wasn't generating the right code when it was just normal. It was not properly cycling through. You got one set of values and that was it. And so we put a circular buffer. Okay. So once we have all of that done and we go and generate it, now how many values did I want of each? 100. Oh, where is it? Yeah, so continuously read 100 values of each using ADC1 and average them. Oh, let's thinking about it. Okay, so unlike before, there's the DMA in it, so it's got this whole setup here. Let me go see if I can go right down to it. ADC1. So some of the things in the ADC, with scan continuous mode, we said enable, continuous conversion mode, enable, DMA continuous requests enable. So that's where all of this stuff is configured. And then we have our two ADCs there. So before in our while one, we did how start IT, for instance, or how start just for our poll. In this case, I said continuous conversions, and you go how ADC start DMA, again, the address, and then data array is some buffer that you're going to point it at, and then 200, because I have 100 of each channel times 2 is going to be 200. So by just doing that, as long as I had everything else configured, let's see where my array is. Um, so I have a data array of 200 uint 32Ts. And the reason I have uint 32T is because when I was over at here, I said word. If I said half word, that needs to be a uint 16T. Because if I tell the DMA controller to move over to the next 16-bit location, and then I store it as 32, then what'll happen is it'll put two 16s in a 32, and you'll get a really, really big number because it won't be leading zeros at the start. So if I did half word and save that space, then that has to be a uint 16T. When you go and compile it, it will give you a little exclamation mark going, you know, my API says it's a 32-bit word, so you potentially are losing data, and are you sure? Okay, that's what the little exclamation mark will tell you if you go and do that. Okay, so let's have a look here, and we will debug. Oh, build might be incomplete. What's wrong? Uh-oh. Yep, go to there. If you get errors ever and it's in stuff you didn't write, like this, it said that there were errors in the USB CDC stuff. I didn't touch that stuff. It's usually it didn't generate properly or didn't complete generating or something like that, and give it another go. Sometimes you have to go project clean in between it. I'm hoping that worked. Mine has a little bit more of a chance of bombing out because I have some of this currently on an SDHC card, so sometimes the timing of it messes up in the generation. So there's my die temperatures and my thermistor temperatures, hopefully. Looks like I'm colder than it is right now. Okay, so I'm gonna stop this for a sec. So that's the first part. Okay, and really the biggest thing, you select all of it, and it's kind of one line of code that you're going to put in there, and you're going to say, go put it in memory. So let me generate it again, actually. Okay, I'll turn it on, and we'll run it for a minute. I'm going to go suspend here for a moment, or pause. Now go over to main. And we could look, for instance, there's data array. And so it shows me a data array, and it says here's 0 to 99, here's 100 to 199. Okay, so there's my 200. And so I can go in there. So I'll go there, and then I will go to, oh, come on, I'll go there and highlight that little thing there. And then it's showing me a bunch of the values. And so it says 3740, 1060, 37.4, 1062, 3741, 1061. So what's going on with this? Yeah, because I have two different channels. Which one is it reading first?
11.
Yeah, that was rank 1, whatever's on input 11. So it's alternating between. Um, if you are not getting values or something isn't going on, you need to run it, pause it, go find the variable, and see if it's filling it out. And so some things that you can get, like for instance, here, I would know that if I had really, really big values, I've probably messed up Word and 16-bit values and 32-bit values, okay, over here. And so we can scroll down through this, go all the way down, and they go, okay, that's good. And then I'm going to open up 100 to 199, if it'll let me. And then we've got all the values going from there, just alternating between. Okay, but that's a nice way of checking in and seeing if things are working. Now I want to, well, let's see. Let's go to here. Really, I wanted a half word. Really, let's go half word. Let's go save. And I'm off to an SD card, so let's hope this works. Okay, go to data console, we turn it on, we'll run it for a little bit. Pause, go to main, find our buffer. Right? Because I stuffed into a 32-bit pigeonhole two 16-bit values. So you get all sorts of weird stuff going on. They got to match. Okay, let's get out of that. Put it back. So that's the first part of the lab. And then what I wanted you to do was use the, I'll just put that. Oh, I could have gone the other way. I could have just gone there. and on there, I should have done that probably. You could go, where is it? Okay, and okay, go back over to main. Here we'll look at array. And so there we have it, but this time we are uint16t. So we've made the match, okay? So it'll all work. What you can get in here when we went through our compiling, let me just stop this. When you went through your compiling, you can get something that will say something like a little warning, and like I say, it says that the results coming back from get value are 32-bit, or the API is 32-bit, and you're storing it in a 16-bit value, and you could get a little exclamation mark over on the side. So that's the first part of the lab. And then what I want you to do is use the little bit more advanced STM32 monitor. So you have to go to ST's site and download STM32 monitor. And there's ones for Mac and Linux and Windows and all of that. And I will just go over to there. I want to just talk a little bit about it. So again, they have they changed up. They had a monitor package, and they completely started again. And they used Node-RED, which is a really, really great thing to be able to do. And so it says introducing STM32 Cube monitor. And so it has kind of a graphical interface similar to kind of Sketch and those kind of things. Again, it's Node-RED in behind the scenes, and you can make desktops that have all sorts of monitoring capabilities. And if you go and look at Node-RED desktops, you'll see all sorts of interesting graphs and gauges and all of those kind of things. So they've integrated that and put some inputs for us to use. So here it's showing, here's how you design up some logical elements, and there's the UI and the graph, and so some gauges and all of that kind of stuff that they have available. As far as inputs, they have inject a signal. They have MQTT, where you can, we'll look at MQTT in the Linux course, machine-to-machine communications, very lightweight way of having devices communicate with each other. There's web interfaces, web sockets, TCP and UDP, and so it gives you options to input in, all sorts of different data, same with different outputs. And then there's all sorts of functions. They have some built-in functions, delays, things like that to switch stuff, range. And they also have a generic function, which is just JavaScript. So if you can write any function in JavaScript, it could go in there. And then you can get it to say, hey, as a result of you getting a certain temperature, send an email. So you could do something like that, or send out a tweet, or something. And so it gives you all of these kind of abilities. So STM32, we've got the application. There's the probe, that's the ST link, and your PC over to a dashboard. So I'll talk a little bit more about Node-RED coming up, but what I want to do is just fire up the monitor just to show you it right now. And so this is how it comes to default. You download it. This is the page that it's on. You can do all sorts of other things and make really, really nice graphs. Now, to start with, what it does is it says, hey, my probe input. Now, it'll say not connected. And I just went like this, and I double-clicked, and then I said set up, and then I had to go and just say find, and it found my ST link. And it knows what serial number your ST link is versus somebody else's. So if you plug in another board, it's going to go, you have to go and search for it and pick the right module. It'll remember the other ones. So it says, okay, I'm just going to go update. The protocol is our serial wire debugging interface, and leave everything else kind of the same, and go done. The output probe, same thing. You have to go through and say, hey, select it, and go find it, and then go done. Now, my variable, so input and output really is what you have. If you look at my variables, it's going to say, hey, what do you want set up here? And I'll click that little arrow, and it wants to know where your ELF file is. That's the executable file with the debug input. And mine happens to be in Workspace, my project, under debug. So wherever your workspace is, that's the name of my project. And then under debug, that's where the file is. So I go up there and I went, hey, copy, and I'll go into the monitor, and then I'll say that's where it is. So I'll go Control V and stick it in there. Once you've done that, then this drop-down box should find the ELF file. And it says, okay, there's where it is. And then it will look at that file. That's the file that it used to program ST-Link and put it on your board. And what it's looking for is the addresses of all the variables. And so most of the time, it's just good like this. But sometimes if you have variables, you might need to expand it, and it'll go through looking a little bit deeper. You have put your variables that we want to look at global, so it should be just in that list, and it's going to give you a better result than if it goes in and out of scope. Okay, and so I've got two variables, and one was called die temperature, and I've selected it, and it knows where in memory it is. It's in my static RAM area at address 224. That's the thing that, when we open up that menu and it says type in a variable or type in the address, that's the address it wants if you happen to know it. But more than likely, we just know what the variable name is. And then the other one I had was thermistor temperature. So I got to go way down looking for thermistor temperature, wherever that is. Okay, and it's at address 220. Okay, and then so I go update, and then I go done. And so any changes and things that you see, it'll put a little blue bubble or something saying those have been updated since you last deployed. If there's something not hooked up, and these are drag and drop things that you can put on, but I'll just go deploy. And so it says successfully deployed. And then so if I click on dashboard, this is the dashboard that they designed. You can do all sorts of fancy dashboards, but this is just a simple chart with a few buttons on it. And then I've got start acquisition. And then, if I put my finger on the thermistor, there it goes. And then if I put, course, I'm colder now then, but there we go. Then this board. Um, so that's got it. And we can just go stop. And again, this is all completely configurable, but that's all I wanted to see. But I'll talk next day a little bit about some more Node-RED abilities. Node-RED's available on Windows. It's available on Linux. I think you can get it on Mac. IBM developed it a number of years ago, put it out for anybody to use. And so on a Raspberry Pi, I've got Node-RED running, and it is grabbing data from different Node devices and updating temperature, humidity in all the rooms in my house. And it's fairly straightforward to set it up and make nice looking user interfaces and things. So we'll talk more about that. But just downloading it, this is the page that comes up. You just have to change a couple of things. Make sure it talks to your probes, and it should be off and running for you. Thanks very much. We'll talk to you next day.